Alright everyone, welcome back to Cody'sLab. So I have an assignment for my geochemistry class in which we take samples of water and we analyze their isotopic composition of the stable isotopes, like the deuterium and the heavy oxygen-18. And we'll end up writing a report about the ratios and how we think they came to be, like how far inland the water came, which is pretty exciting. But a couple of days ago I learned that we students are actually able to bring in samples of water to do the project on. So our assignment actually includes going out and collecting samples of water. Now, of course, the professor is expecting us to get like samples from our, a pond or a river, or perhaps just our tap water. But I thought I'd take it one step further and actually use a sample that I have intentionally enriched in the heavy isotope. Now, many of you remember my Making Heavy Water series, which was a 5-part series that I did over a year ago now, which I spent 3 months creating a sample of water which was pure, but it contained enough of the heavy isotopes that it was able to sink in normal water, which means I had enriched it with at least 80% of the heavy deuterium isotope. Of course, I may have also enriched it in the heavy oxygen, which would mean it gets complicated quickly. Unfortunately, I do not have that sample anymore. You see, I left it in the dash of my truck, and the vial leaked out, and the water evaporated in the hot car. And I tried to use a desiccant to absorb it from the air, but I ended up losing the entire sample, unfortunately. So basically I'm going to have to start over. And another problem is that I only have 5 days to do it now, because the samples are due on Friday next week, and it's, well, Sunday afternoon now. So I guess this is actually going to be a little bit of a challenge for me to see how much I can enrich the heavy isotopes in as little time as possible. So a few things that are different from my last experimental run is, instead of using the batteries, I'm going to be using a known isotopic source, such as this Fiji water here. I know, bottled water, super evil, but it does all come from the same place and it's very well known. So I can use this as like a standard isotope, and I can measure the amount that I increase it from here. Also, I'm using solar panels for my electrical source. Now, unfortunately, this here is not really working fast enough. See, I'm pumping 200 watts into here, and it's producing lots of gas, and it's consuming nearly 50 milliliters of water per day. The only problem with that is that 50 milliliters per day is not going to destroy even 1 liter by the time that I have. So I'm going to have to find something a little bit faster. Now, I've done a little bit of thinking about this, and I think I've come up with a solution. You see, what can I do to basically simulate electrolysis, but on very high, speed? And I figure actually using a reaction between aluminum, see, I got some aluminum foil here, and some sodium hydroxide, is basically, it's very similar to the electrolysis reaction. It's still going to favor the light hydrogen isotopes being turned into gas and the heavier isotopes staying in the liquid. I found a research paper on this, which I'll link in the description, in which they've experimentally found that the ratio between the heavy and light isotopes is about 5. So it means that there's going to be 5 times more of the heavy hydrogen in the liquid than there is escaping in the gas, which is not quite as good as electrolysis. So I was figuring I was getting a separation factor of like 8, but 5 versus 8 is pretty good. The separation factor with distilling the water is only like 1.05, so this would definitely get me somewhere. And the most important thing is, this reaction is very fast. In fact, I'm going to have to slow it down so I don't boil all my water off. Now, I know a lot of you are going to say, but Cody, why don't you hook it up to your 1.81 kilowatt solar panel array you got back at the ranch? Well, there's 2 problems with that. One, I'm not back at the ranch right now, and I don't expect to be for another week. And 2, my parents kind of need the power. I can't just take it all. But if I did, I could destroy probably an entire gallon of water in that 5 days of time. But this makes it a little bit more of a challenge, I guess. Now I've got the sodium hydroxide in, it's time to add the Fiji water. So it has just occurred to me that the sodium hydroxide contains hydrogen. So I'm contaminating my Fiji water with hydrogen from the sodium hydroxide, which means I'm going to have to take a sample of this that's mixed up. And if I ever get the chance, I need to run an isotopic analysis on this. That's 1 pound of sodium hydroxide and 1.5 liters of Fiji water. Now that this has come to a chemical equilibrium, I'm going to pour off a little bit into the sample cup. That way I've got it for later reference. Ooh, that was quick. Alright, I probably ought to let it cool off again before I add any more, because it's starting to vaporize a little bit of water out. I don't know if you can see. Did I really just do that? Look at this. It was getting a little too warm and was making steam again. And so I put it into this bucket of cold water to cool it, to recondense the steam and so I don't lose as much water vapor. Well, you can kind of see what happened. Looks like I'm starting again. Okay, so it's the next morning and I've reset with another jug, and I'm using smaller batches this time. That way it's don't have quite so much going off all at once. So there's 500 milliliters and half a pound of sodium hydroxide in here right now. Also, you'll notice I've got this copper tube coming off of it, and that'll collect all the vapors, and hopefully by the time it gets way down there it'll be condensed into a liquid. I'll capture it into that jug, and then at which point I can put it back into the system. Anyway, let's get to putting those aluminum pieces back in and see how this turns out. I'd say this is working pretty well. You see, I can put the aluminum in much faster now because I'm not too worried about the water being lost, because you can see I'm capturing it right here. I did have to use this tank of water though to try to help cool it, because it was producing too much heat for the copper to dispel. But once I got that water in there, it's doing pretty good. So after letting it sit and do its thing, I'm now left with a jar full of this black sludge. I think there's still some aluminum left over, and certainly there's water left over, but that makes sense because I only added half a pound of this, which theoretically could have been completely destroyed or used up by about 200 grams of aluminum, which is less than what I put in there. Now I got to figure out a way to distill this off. I'm thinking maybe I could actually put this down into a double boiler with some oil or something and just boil it off through this copper tubing. So yeah, I broke another bottle, as you can see. So I've wisened up a little bit, and I got me a kettle here. This way I can actually heat it without worrying about it shattering. And it's stainless steel, so it'll resist the corrosion of the hydroxide. Yeah, still dangerous, but much safer. You know, I think this round was much more successful. You see in there the dried material? There's a couple of foil balls that didn't dissolve, but I think overall that went pretty well. I managed to acquire this much water right here. Let's add this to the stuff that we got before. That's 250 milliliters. Very nice. So it means I got 150 milliliters in this round, which is a little bit better recovery there. This is not exactly easy to clean out, but I'm going to call that good enough. Let's pour some more water in it. Okay guys, we're almost done with this step. As you can see, I'm distilling off some water, and this is the stuff that has been treated with the lye and aluminum twice now. So yeah, this was 2 liters of water, and now it's looking like I'm going to get less than 200 out of it. So here's a brief synopsis of everything that I've done so far. See, I had 500 milliliters of water combined with 200 grams of sodium hydroxide. That yielded 100 milliliters of H2O that I distilled out and saved. The next time I got a little bit better, and I got 150 milliliters. And the next 2 times I noticed that the amount of sodium hydroxide was actually quite excess. In fact, the stuff I was washing out of the pot was still highly basic, so I added less hydroxide and I got the same amount of water. So I combined all the waters together into 500 milliliters, basically did this once again with 100 grams of sodium hydroxide, and I gained this water right here. There we go. You see, I've got the equation here that was the chemical reaction, and the amount of each reactant that I had. You know, 500 milliliters, 27 moles. That's quite a few moles of water, yeah? Now, the aluminum was in excess, and certainly the water was in excess, so it means that the limiting reagent was pretty much the sodium hydroxide. But that's not even actually true. It's actually the limiting was the amount of sodium aluminate that could dissolve into the water, which apparently wasn't all that much. But let's just assume this is right, that I reacted 2.5 moles. That means that only 2.5 moles of water were destroyed, or about 60 milliliters were used up in the reaction. That means I've lost 290 milliliters of water. I thought I was being really careful with it, you know, trying to recover it using the copper tube and sealing the vessel and everything, but that quantity of loss does seem to make sense because this isn't very sophisticated apparatus. I mean, look at it, it's a tea kettle and a fish tank. Perhaps if I do this again it'll be a little bit better, but yeah. But I should still have increased the deuterium content on this. At least a little bit. Not as much as I was hoping for, but it should be at least concentrated a little. And I will take a sample of this and hopefully I can get that analyzed as well. Okay, so here we are. I've got a little jar set up. The electrodes are lead and I've got 12 volts hooked to them, and I can supply up to 40 amps. So here's our water. Let's put this in. Now since it's mostly pure water, it shouldn't really be doing anything right now. And indeed it isn't. Alright, a little bit of acid. It should start to fizz almost immediately. Okay, this thing's already starting to heat up, so I better build a housing for it and a cooling bath. Reaction vessel down there with the electrodes going in. 10 amps of current, 12 volts, that's 120 watts. And I got this cooling system set up. You can see there's a pump there, and this tank with water, and about 30 feet of hose out that direction. See? And then it comes back around. Also, I've got a reflux system set up. See this tube here? That's to catch all the water vapor that comes out of the reaction vessel. And of course, that goes out to a separate collection to catch any drops that make it all the way through. Okay, so I'm down to just 12 hours before the water sample is due. Looks like I got, well, that much there. I mean, I got rid of that much. So I'm just going to distill the water out into this little cup. So I remembered to distill out the Fiji water and sodium hydroxide mixture. That way I get rid of the sodium hydroxide. So I thoroughly cleaned and dried this thing, and now I'm running that sample. Just so I got something that's actually just pure water. So judging by the foliage behind me, it's been about a month since my last clip, but I now have the results of the experiment. Unfortunately, the professor did not allow me to film inside the lab, so there won't be any awesome laboratory footage. So I'll just have to explain what I did here and give you the results. So the first thing we did is we put about half a milliliter of our water sample into a little test chamber. Then we added a little rod that contained a bit of platinum catalyst on it. The platinum catalyst allowed the water vapor to exchange hydrogen atoms with the hydrogen that we injected into the sample. After about a day or so, this came to equilibrium. We then took that gas and injected it into the mass spectrometer, where the hydrogen gas was ionized, accelerated down a tube, and deflected by magnets. The lighter ions were deflected more than the heavier ions. The separated hydrogen ions would then collide with these little Faraday cups, which would detect a voltage and be able to count the ions. Out of the 40 or so samples that the class was able to do, I managed to talk them into letting me do 4 of my water samples. I got a sample of battery water, which was only 2 years old. My final water that I did processed in my video, with the electrolysis and everything. I had my sample from the aluminum process, and the sample that came from the sodium hydroxide. In order to protect the Faraday cups so that I didn't get too much voltage on one of them because I've enriched the isotopes, I diluted the water with an additional 50% of its own volume with Fiji water. And once we got into the lab, we diluted them all once again with 50% of their own volume, but this time using laboratory distilled water. So here's the part per million values straight from the reactor after I've removed the dilution factor. And here's the enrichment factor over SMO, or the standard mean ocean water. The battery water had about 1.4 times. The water that I started with the sodium hydroxide, had about 0.98 times SMO. I had enriched that to 1.8 by using the aluminum process. And the final electrolyzing brought it up to 2.6 times the standard mean ocean water. One interesting thing I discovered from this was the fact that the lye that I used had already been enriched to about twice the mean ocean water standard, which means that the process they used to make the lye must have enriched the hydrogen isotopes somehow. Not a lot, it was about twice the normal level, but that definitely meant that when I mixed the lye in with my water, I had already increased the concentration right there. But of course, the results that I got from the aluminum process were actually more than what I would expect just from the straight up mixing of the lye. So the aluminum reaction did in fact enrich the hydrogen isotopes. It's a very inefficient process, and it would have been better for me to have just taken the lye, reacted it with a strong acid, then distilled off the water. But there you go. So for this data, it appears that the batteries, the lead acid batteries hooked to a solar panel and being charged constantly, seem to increase the deuterium concentration by 20% per year. Extrapolating that to 5 years, that means that the batteries that I started with in my heavy water project last year must have had about twice the normal deuterium concentration. One thing I did find that was odd from this data was the fact that the separation factor of the electrolysis process wasn't that high. It was only like 1.55 or something. And I expected something higher, like 8 or 10. And what I think might have caused this is water actually boiling out of the reaction vessel without being electrolyzed. Because I was trying to do it so quickly. I was putting so much power into there that even with my precautions, a lot of the water was just escaping as water vapor. Or it could be that the mass spectrometer we're using just couldn't measure those high values accurately. Anyway, I got a lot of good data, had a lot of fun doing this. Hope you guys enjoyed watching. I'll see you next time.